All right, so basically we're going to now start talking about electrons. Now, the thing to remember, guys, about electrons is when we talk about electrons, what we know at this point is we know we have protons, we have neutrons, we have protons, neutrons, okay, and we know that they are surrounded by electrons, but there's no real structure to the electrons, okay? So that's what this is about. So, background real quick reminder about waves. Wavelength, simple distance trough to trough. Amplitude is simply the size of the wave. If you listen to AM radio, that means amplitude modification, so it's adjusting the amplitude, the size of the wave that way. Frequency is the other thing. Now, for us, what we really care about is wavelength and frequency. That's really what we're going to be manipulating. Now, frequency is simply the number of waves. Okay, not difficult to figure out that this is the lower frequency and this is the higher frequency, simply because there's more waves in the same time period. Now, typically when we talk frequency and we talk waves, we're dealing with what are known as units of hertz, which is a number per second. Okay, you will also see this written as seconds to the -1, because remember, a negative exponent simply means division. Wavelength is always in meters. Okay, so just keep that in mind. Now, the reason we care about this is the electromagnetic spectrum. Now, this is similar to a diagram in your book. You need to copy this from your book into your notes. And there's a couple of points you want to pick up on. First, speed of light. All of this, the entire electromagnetic spectrum, goes the speed of light. Everything on here, gamma rays or radio waves, go 3 × 10⁸ meters per second. Okay? In other words, how we get that is the speed of light is wavelength times frequency, lambda nu. Okay? Again, meters times 1 over a second. Okay? I'm going to get meters per second. Now, the other thing to pick up on is how wavelength and frequency are inversely related. Notice that as wavelength increases, my frequency is decreasing. And that's a real important thing to pick up on. And this ties into where we're going. All right, so the reason that we have to talk about that is the first thing we discover is that when we talk about light as a wave, there are certain things we can't explain with light as a wave. And one of those things is that hot metals glow. Why would hot metal glow? I mean, really, if you think about it, why does it glow? It's not phosphorescent, it's not luminescent, it shouldn't glow at all. So there's something going on. And how this was explained was by Max Planck. And what he basically said is, okay, there is an energy packet associated with this. He called it a quanta. Well, Einstein took it one step further. And what he said is, okay, the quanta is actually light. Okay, so what he did is he discovered the photoelectric effect. And this is actually what he got his Nobel Prize for. But in essence, the photoelectric effect is what we already observe when you look at photosynthesis in plants. Okay? When you observe photosynthesis, light comes in. Remember, it caused an electron to gain energy. Well, that whole ability of light to cause an electron to gain energy, that's what's the basis of the photoelectric effect. Okay? So,
when an electrode in an evacuated tube, as shown here, is coated with an active metal, electrons may be emitted from the metal when it is irradiated by light. This effect is called the photoelectric effect.
Okay, in essence, what that just said is it's just saying irradiated light's been shown on the metal, okay?
Einstein explained the photoelectric effect by using Planck's concept of light as a stream of photons. When light of long wavelength impinges on the electrode...
Okay, so pause real quick. The string of photons, that's Planck's quanta. That's his little packets. So this is where we start getting the term photon from as well. Let's back that up just a...
No electrons are emitted. Einstein proposed that this is so because the individual photons do not have sufficient energy to dislodge an electron from the attractive forces of the metal. Even when the light intensity is increased, there is no emission of electrons and no current flows. When light at shorter wavelength strikes the surface, electrons are emitted and are drawn to the anode. Thus, a current is seen to flow. Einstein proposed that the photons of shorter...
Sorry about the technical difficulties, guys. Let's try one more time. About there.
When light at shorter wavelength strikes the surface, electrons are emitted and are drawn to the anode. Thus, a current is seen to flow. Einstein proposed that the photons of shorter wavelength light impart sufficient energy to the electrons to enable them to escape from the metal.
Okay, in essence, the shorter the wavelength, the more it could impart energy to an electron and it would gain energy. That's in essence all he was saying. Now pay attention to what happens to the number of electrons as this continues playing as we increase the amount of light, and listen to what they say about energy. Don't let the jargon fool you. Pay attention to what they say about the energy. The actual energy of the electron is still constant. It still gains the same amount of energy. It's just more of them gaining, okay? Hello? There we go.
The kinetic energy of the electrons is the excess of that which they require to escape from the metal. When the intensity of the shorter wavelength light is increased, more electrons are emitted, and the observed current increases. However, the excess energy which the electrons possess remains the same. A higher intensity of light increases the number of electrons emitted, so the current increases. However, because each photon still imparts the same energy to each electron, the kinetic energies of the electrons remain the same. When light of still shorter wavelength is employed, the electrons are emitted from the metal with higher kinetic energy. This is so because the higher energy photons have imparted more energy to the electrons, and more kinetic energy remains after they escape from the metal.
Okay, so in essence, guys, what we discover, what we discover is that what we're seeing is that there is a connection between energy and frequency, okay? And we explain this in terms of this right here. We have Planck's constant times frequency, speed of light, all of this. What you want to be able to do within your notes is also show these as combined. Okay, notice it's basic math. They share the same, okay, they have something in common. So you're going to need to solve this and show this as where you have E equals and show a combined equation here. But the point for now is that energy, wavelength and frequency are inversely related, but energy and frequency are directly related. And this is important when we go to actually calculate the amount of energy in a specific amount of, or in any photon.